So the next is some basic relationships between pixels. So what do you mean by a pixel? We know that digital images are composed of a finite number of elements, each of which has a particular location and value which we call as a pixel, or this is also called as picture elements, image elements, pels and pixels. So usually the most widely used term is the pixel. Okay. So if suppose this is an image so if this is an image plane, then it has some number of rows and some number of columns, and here it has some finite number of elements, each of which having a particular location and value, which we call this as a pixel. So each and every box here represents a pixel. So each pixel will be having a particular location, and the location of this first pixel is first row, first column, so 0, 0, and the intensity of this pixel, the value of this pixel is nothing but the intensity level at this particular point in an image. Okay, this is what is a pixel in an image. Okay, so now here in this particular topic we are studying some basic relationships between the pixels. So under this, first is the neighbors of pixel. So now to illustrate the neighbors of pixels, first let me consider a pixel P. Okay, so let this be a pixel P. So it is having some coordinate value x comma y. Okay, so here there are three types of neighbors. The first one is 4 neighbors, 4 neighbor representation, that is n4 of P anta kariteve. Okay, so which we call as n4 of P. Okay, so here the 4 neighbors of this pixels are the 2 horizontal neighbors and 2 vertical neighbors. Okay, so if Q is the another pixel which is at this location, and we say that Q is 4 neighbor of P. Okay, so the location of P is x comma y. So what would be the location of Q? Here this is next column, same row. So x comma x y plus 1. Right. And now what is the location of this particular pixel? It is equal to x plus 1 and same column y, and the location of this pixel is x minus 1 and x is same and y minus 1, and the location of this pixel is x minus 1 and same column. So this is how we represent the pixels. So the 4 neighbors of pixel P are Q, R, S, T. So this is equal to Q, R, S, T. So that means 4 neighbors of pixel P is equal to x minus 1 comma y, x comma y minus 1, x plus 1 comma y, x comma y plus 1. So these are the 4 neighbors of pixel P. So if Q lies here, so this is the value of Q, then Q is 4 neighbor of P. Okay. So also we have diagonal neighbors of P, which we call as NDP, diagonal neighbors of P. So the diagonal neighbors of P are the 4 diagonal pixels here. Okay. So this pixel, this one and this one. So what are the location of these pixels? I should have shown in big image. So if this is P, its coordinates are x and y and its 4 neighbors are Q, R, S, T and its values are x comma y plus 1 and x plus 1 comma y, x comma y minus 1 and this is x minus 1 comma y. Right. So these are the 4 neighbors of P. Now let me consider the diagonal neighbors of P. So diagonal neighbors of P be 1, 2, 3, 4 and the coordinate values of this are next column, previous row. So x minus 1, y plus 1. So next row, next column, x plus 1, y plus 1. Previous column, next row, previous column. So here previous row and previous column. So this is how the 8 diagonal neighbors of P are represented. So 8 diagonal neighbors of P are 1, 2, 3, 4. So which are, so x minus 1 comma y minus 1 and x plus 1 y minus 1, x minus 1 y plus 1, x plus 1 y plus 1. So these are all the 4 diagonal neighbors of P. So also there is another representation, that is 8 neighbors of P. 8 neighbors of P means it is the combination of 4 neighbors of P plus the diagonal neighbors of P. That means if at all we talk with respect to sets, it is equal to 4 neighbors of P union of 8 neighbors, diagonal neighbors of P, which is nothing but 8 neighbors of P. So this 8 neighbors of P is a set which includes Q, R, S, T, 1, 2, 3, 4. So this is what is 8 neighbors of P. So there are 3 types of representation: 4 neighbors of P, diagonal neighbors of P and 8 neighbors of P. If Q lies in this set, that is 8 neighbors of P, then Q is 8 neighbors of P. This is how we call. Okay. This is all about the neighbors of pixels. Adjacency, connectivity, region and boundary. So next is adjacency, connectivity, regions and boundary with respect to pixels. So to understand the concept of adjacency, there are 4 types of adjacencies here. So the first is 4 adjacency, 8 adjacency and M adjacency. So, to understand this adjacency concept, let me consider an example where you have these pixels. So, consider this pixels. Now, this is a binary image, okay. So, this is a binary image, each of which we call a pixel. So, this binary image is having only two intensity values, that is 0 and 1, okay. So, let me consider the pixel P, and if I consider another pixel Q, to say that Q is adjacent to P, first thing is that there are two conditions. First condition is that Q and P should be having the same value which is in the subset of V. So, the P and Q should be having the same value, and here in this case V is equal to 1. Since it is a binary image which has only the two intensity levels. If suppose I consider the image of having 256 levels, then V can be the subset of this 1 to 10, anything like that, okay. So, first condition is that in order to say that Q is adjacent to P, the first thing is that both P and Q should be the subset of this V, okay, should be having the value of this subset V. Next condition is that in order to say that this pixel Q is 4 adjacent to P, then this Q should be in 4 neighbor of P, should be in the set of 4 neighbor of P, okay. So, if this Q is in the set of 4 neighbor of P, then we say that Q is 4 adjacent to P. That means if this is Q and this value is 1, then the 4 neighbors of P are then the 4 neighbors of P are B, D, Q, G, right, B, D, Q, G, and among this only B and Q are having this subset value. Therefore, B and Q are 4 adjacent to P, okay. So, now next, in order to illustrate 8 adjacency, the first condition is that P and Q should be having the value of this subset V, and the second condition is that Q should present in 8 neighbor of P, in the set of 8 neighbor of P, okay. So, what are all the 8 neighbors of P here? Can you say A, B, C, D, E, Q, F, G, H. So, these are the 8 neighbors of P. So, now here Q, B and H are having Q, B and H are having the same value as that of P, and which is as in the subset V. Therefore, I can say that B, Q and H are 8 neighbors, 8 adjacent to P. So, I can say that B, Q and H, B, Q and H are 8 adjacent to P, okay. And the third is M adjacency. In order to say that this is Q is M adjacent with P, there are two conditions. First is the Q should come in N4 of P, and second condition is that Q should come in N diagonal of P. So, the intersection of this N4 and ND should not contain the value which is in the subset V. Then we say that as M adjacent. So, this I can illustrate with an example. So, with an example I will illustrate M adjacency. So, let me consider these pixels. So, in order to illustrate M adjacency these adjacency concept, first I should also tell about the connectivity. Okay. So, that means the two pixels P and Q are said to be connected if there exists a path between P and Q. Okay. So, the path can be of any type, like 4 adjacent path or 8 adjacent path or M adjacent path. Okay. So, here this is pixel P, and this pixel, the path of this P with this pixel is 4 adjacent path, and this pixel is in 4 adjacent with this pixel, right, and this pixel is in 8 adjacent with this pixel, and this pixel is also in 8 adjacent with this pixel. So, these two pixels are said to be connected if these two are having the same values and there exists a path between these two pixels. Okay. So, now here there is 4 adjacency, here also there is 4 adjacency between these two, and here there is what, 8 adjacency, and there is 8 adjacency. So, if suppose whenever you have ambiguities like this, whenever you have two paths from P to Q like this, then always what we prefer is the 4 adjacent path. Okay. So, this is of first preference. So, this path we call as M adjacent path. Understood? So, whenever you have ambiguities, whenever you have two paths, then always we prefer 4 adjacent path. Okay. So, this is the M adjacency. Okay. So, next is regions. So, in order to illustrate regions, let me consider another example. So, 0, 1, 1, 0. So, a region is defined as it is the subset of pixels which is present in the entire image. Okay. So, the subset of pixels which forms connectivity among themselves is represented by a region. So, here there are two regions, region I and region J. So, these two regions are said to be adjacent region if suppose they are connected, there is a connectivity between these two regions. That means if there any path exists between the pixels of these two regions, then we say that these two regions are adjacent regions. If there is no connectivity, either 4 adjacency or 8 adjacency or M adjacency, if it does not get connected with any of the adjacencies, then we say that these two are disjoint regions. Okay. So, these two are disjoint regions when there no connectivity establishes between the two regions. If the connectivity establishes in either of the ways, 4 adjacents, 8 adjacents or M adjacents, then we say that the two regions are connected and they are adjacent to each other. Okay. So, next is the boundary. Boundary means if suppose you have an image, So some of the pixels lies at the boundary of the image. So these are boundary pixels. So these are all boundary pixels. Okay. So there are boundary regions also. So we say a region is a boundary region if that region lies at the border or contour of that image, and if this region contains at least one pixel which is of background intensity. Okay. So if this region contains at least one pixel which is of background intensity, we say that as a boundary region. Okay. So now you understood the adjacency, connectivity, region and boundary with examples. Right. So next is distance. Distance measured between pixels. So next is distance measures. So here in this topic we will study how to measure the distance between the two pixels. Okay. So to illustrate that, let me consider the three pixels P, Q and R. Let this be having the coordinates, and these pixels are located at XY, ST and MN. Okay. So now here in distance measure, there are some set of functions in order to find out the distance between the two pixels. Okay. So here there are many number of pixels. Let this be P and this be Q. So in order to find out the distance between this P and Q, okay, so we will be using this distance measures. Okay. So now here there are some functions in order to measure the distance. The first is that, so the distance between P and Q is always greater than or equal to 0. If the distance between P and Q is equal to 0, then it means that P is equal to Q. Right. So if the distance between P and Q, the distance between P and Q should be always equal to greater than or equal to 0. If the distance between P and Q is equal to 0, means P and Q exists at the same place if the distance between P and Q is 0. Right. Next, the distance from P to Q is same as the distance from Q to P. Right. So if suppose I consider this is the shortest distance between P and Q. If the distance between P and Q is 2 and the distance from Q to P is also 2, it must be 2. Right. And the third function is that the distance between P and R is greater than, is less than or equal to distance between P and Q plus distance between Q and R. If suppose I consider this, right. So this is Q, this is R. Okay. So now the distance between P and R is smaller than the distance between, the sum of distance between PQ and distance between R. The sum of the distance PQ distance plus QR distance is always greater than the PR distance, right. So that is what this equation means. So these are all the some functions of distance measures. So now in order to measure the distance, there are three different types of measurements. First we go with Euclidean distance measurement. So Euclidean distance. So in this approach, here we measure the distance between two pixels by using the formula distance, Euclidean distance between P and Q is equal to square root of, what are the coordinates of P? It is x comma y, coordinates of Q is s comma t. So x minus s and x y minus t. So using this formula we find the Euclidean distance between the two pixels P and Q. Okay. So the next type is for distance, or this is also called as city block distance. So here in this, in order to find out the distance between P and Q, we use the formula, that is magnitude of x minus s plus magnitude of y minus t. Okay. So this is what is for distance. For example, when do we say that, let me consider an example. So now look at this. So these are all pixels, okay. So this pixel is having intensity value 0, this pixel is having intensity value 1, and this pixel is having intensity value 2. Suppose now let this pixel be P and let this pixel be Q. When do we say that Q is for distance of P? So if d4 of P comma Q is equal to 1. Let us say that each and every pixel is having unit distance between them, okay. So now Q is the for distance of P if at all you consider the 4 neighbors of P, right. So all the 4 neighbors of P is having the unit distance 1. Okay, then the distance of Q is equal to 1. So Q is for distance of P means then Q should lie among the 4 neighbors of P. It should lie in the set of 4 neighbors of P. When Q is equal to 1, then we say that Q is for distance of P. That means Q should lie among the 4 neighbors of P and the distance of 4 neighbors of P is 1. Okay. If at all I say the distance of Q is 2 from P, then it means that the Q lies on the second contour, that is these values are having the distance 2 from point P, center point P, that is center pixel P. So Q must be 1 among these pixels. Okay. So this is how we find out the distance of Q from P. If distance of Q is 1, then this lies in the first 4 neighbors, and if Q is equal to 2, then Q lies in the second 4 neighbors of P. Understood? So always this structure leads to rhombus kind of contour. Okay. So next is aid distance. So here let me consider this example. So, this 8 distance of P can be calculated with the formula d8 of P, which is equal to maximum of x minus s plus magnitude of y minus t. So, this is the formula which is used to find out 8 distance of P. This is also called as chessboard measure, chessboard distance. So, here in this, if Q is equal to 1, this means that Q lies within the 8 neighbors of P. That means Q must be one among these particular pixels. Okay. If the distance of Q is equal to 2 from P, then it means that Q must be one among these pixels. So, here the contour of these pixels will be in square form. Okay. So, we know that the 8 distance of P means, so here we will usually consider the 8 nearest neighbors of pixel P in order to find out the distance of Q. So, if Q lies here, we say the distance of Q is 1. So, Q is 8 distant of P, and if Q lies here, then we say that Q is equal to 2, which is 8 distance of P. So, that means it comes in the second 8 distance of P. Okay. So, this is all about the distance measure. So, in order to find out the shortest path between the two pixels, so let me consider an example to illustrate that. So, in order to find out the shortest path between the two pixels, I have considered an example. Here in this, there is a set of pixels. So, it has the set of pixels contains P, P1, P2, P3, P4. Okay. So, now I have to find out the shortest path, the shortest distance between P and P4. So, in order to find out the shortest between P and P4, first let me consider that the condition is that P, P2 and P4 are all having the same intensity value 1. Okay. And let P1 and P3 be 0 or 1, it can be anything. Okay. So, in order to find out the path between P and P4, we know that P, P2, P4 are 1 and P1 and P3 can be anything. It can be either 0 or 1. Okay. So, now let me consider the case 1. Let P1 is equal to 0 and P3 is equal to 0. So, now since it is 0, this is also 0, this is also 0, the shortest path between P, P2, P4 is this, right. So, it appears like this 1, 0, 1, 0, 1. So, the nearest diagonal neighbor, so this is the diagonal neighbor of pixel P. Okay. So, the shortest path is between P and P4. P, P2 and P4. So, this is the shortest path. and let the distance between each pixel be is equal to 1, therefore the path is 2. Okay. Now let me consider the second case, case 2, where P1 is equal to 1 and P3 is equal to 0. Now if this P1 is equal to 1, now to find out the shortest path between that, so this is the 4 adjacent to this P and this is 4 adjacent with this is 8 adjacent with this, therefore the path is like this: P, P1, P2, P4, and the distance is 1, 2, 3. Right. So next consider the next case, second case, case 3. Let P1 is equal to 0 and P3 is equal to 1. So now consider this case. So P1 is equal to 0, this is 0 and this is equal to 1. Okay. So this is M adjacent, sorry, this is 8 adjacent with this and this is 4 adjacent with this and this is 4 adjacent. So the path is P, P2, P3, P4. So the distance is 1, 2, 3. And consider case 4. Let P1 is equal to 1 and P3 is equal to 1. So look at this case now. So all these are 1. So now this is 4 adjacent with this is 4 adjacent with this is 8 adjacent with this, 4 adjacent. So whenever you have ambiguities like this, whenever you have two paths, so you always have to choose the 4 adjacent path. Okay. So now the distance is, the path is from P, P1, P2, P3 and P4 and the distance is 1, 2, 3, 4. So now which is the shortest path between P and P4? When P1 and P3 are 0, the shortest path between P and P4 is 2. Right. So the shortest path between P and P4 is 2, that can be achieved when P1 and P3 is equal to 0. This is how you can find out the shortest path between the two pixels. This is the last topic of this particular module. Okay. So here we will understand the concept of linearity and non-linearity. Okay. Now let me consider an example where, if at all I consider an image f of x comma y, after processing this image, after performing some operation on this digital image, it produces the output. I am performing some operation h on this input image and this produces the output g of x comma y. Okay. So this can be represented as, this h can be any operator. So when performing some operation h on this input image f of x comma y, this produces the resultant image, that is g of x comma y. Okay. This I call as equation number 1. Okay. So now to understand the concept of linearity, if this h is a linear operator, then performing linear operation on So this is the condition of linearity. Now here I have considered the two input images f1 and f2. These two are having the same size. Okay. So a and b are the constants. Okay. And now performing linear operation on these two images, it should result with the equation such that it is equal to LHS. Okay. So that means here reducing this step. Now I am going to reduce this step. So performing some operation on the input signal f1 of x comma y. So I am performing some linear operation on the input signal f of x comma y. It results with g of x comma y. If I perform the same operation on f1 image, then it should result with g1 as its output, g1 of x comma y. Now I am performing same operation on the second image, that is f2. So when compared to equation number 1, this should result with the output g2 of x comma y. Okay. So if this is same as, this RHS is same as LHS, then we say that this operator H is a linear operator. Okay. So to illustrate this, let me consider one example. Okay. So to illustrate linearity, let me consider an example where H is a summation. This is to illustrate linearity. Let X be the summation operator or summing operator. Okay. So now I will use this operation on the two input signal f1 and f2. Therefore, summation of a into f1 of x comma y plus b into f2 of x comma y is equal to a into summation f1 of x comma y plus b into summation f2 of x comma y. Okay. So now comparing this equation with equation number 1. So here H is nothing but summation. So a into summation of f1 of x comma y results with g1 of x comma y. Okay. Next, b into summation of f2 of x comma y is equal to g2 of x comma y. Okay. So which is equal to, so if this LHS is equal to RHS, then we say that the linearity holds good for summation operation. Okay. Okay. So to illustrate nonlinearity, let me consider the H operator as the maximum operator. Okay. So in my previous thing, I considered the example of summation, which proves that the summation operator is a linear operator. So now to illustrate nonlinearity, I have considered the maximum operator, and again here I am considering the two input images f1. Let this be 0, 2, 2, 3. Six, 5, 4, 7. Let this be 0 to 2, 3 and f2 is equal to 6, 5, 4, 7. Okay. And let a is equal to 1 and b is equal to -1. Now consider the linearity formula, that is maximum of a into f1 of x comma y plus b into f2 of x comma y, which is equal to a into maximum of f1 of x comma y plus b into maximum of f2 of x comma y. Okay. So now substitute the values of A, B, F1 and F2. So maximum of A is 1 and F1 is 0, 2, 2, 3. B is -1 and F2 is 6, 5, 4, 7. So this is equal to A is 1 and maximum of, what is F1? 0, 2, 2, 3. And maximum of B is -1 and maximum of F2. What is F2? 6, 5, 4, 7. Right. So now let me simplify this. Maximum of 0, 2, 2, 3 plus -6, -5, -4, -7, which is equal to, now which is the maximum value in this matrix? So maximum value is 3. And now which is the maximum value in this matrix? The maximum value is 7. Right. Now simplifying this further. So -6 plus 0 is -6, -5 plus 2 is -3, -4 plus 2 is -2, -7 plus 3 is -4. Right. So this is equal to 3 minus 7. So further simplifying. So which is the maximum value in this particular matrix? So since all are negative numbers, so the maximum value is -2. Therefore LHS is equal to -2 and RHS is 3 minus 7 is 4. And LHS is not equal to RHS. Hence maximum operator is non-linear. Okay. So that's all about module 1. In my next class I will be starting with module 2. Thank you.